Dear students, in this section we are going to discuss reflection and refraction of a travelling wave which incident on a boundary of two mediums. Here we will learn how to calculate the amplitude of the reflected and transmitted wave and also how to write the corresponding equations. Here first we are going to develop the theoretical or conceptual part, then we will learn the concept application part through some selected illustrations. So, let us develop the conceptual part first. Suppose a travelling wave, suppose a plane progressive wave is travelling from left to right and incident on a boundary of a two mediums, right. Suppose this is medium 1 and this is medium 2 and this is the boundary of two medium and this is the incident wave. And this wave is travelling from left to right. Suppose this direction is the positive x direction, we can define the equation of this incident wave. Suppose we can write the equation of this wave as y equal to ai sin omega t minus kx, right. This is the equation of the incident wave or travelling wave. You can observe here we put the negative sign between the omega t and kx term because wave is travelling in the positive x direction and here ai is the amplitude of the incident wave, right. Now, what will happen? The certain part of the wave will transmit it to the medium 2 and certain part will reflect back like this. Okay. In this way, you can say in the medium 1, we have the two waves, two type of the waves. One is the incident wave because waves are the continuous one. That means the wave is coming from left to right and this wave, that the reflected wave, is coming from or moving from right to left, and this transmitted wave will move in the leftward direction or you can say in the positive x direction. So, let us define the equation of the reflected and transmitted wave. Let us write the equation of the incident wave again. This equation is the y incident equal to a I sin omega t minus k1x. Omega is the angular frequency and k1 is the wave number of the medium 1, right. This wave number depends on the angular frequency as well as the medium property. Medium property is a solely factor of the wave velocity. That means, wave velocity depends on the medium property. That means, in particular medium, if we say in medium 1, the value of k, that is the wave number, will be constant. Similarly, we can say in the medium 2, the value of k or wave number will be constant. And this part, that is the angular frequency, that will remain unchanged while wave move from medium 1 or medium 2 because frequency remain unchanged. Okay. And now, let us consider the boundary again. This is the reflected wave. Now, you can observe this reflected wave is moving in the left direction, that is in the negative x direction, and it is moving in the same medium. That means, the value of k will not change, value of omega will also not change, but there will be one change, that is negative. In place of the negative sign, we will put the positive sign because wave is travelling in the negative x direction. And one more thing will change, that is the amplitude. Amplitude of the reflected wave is the AR. Okay. Now, let us consider the transmitted wave. Transmitted wave is travelling in the medium 2, correct, and this is positive x direction. That means, there will be no change of the sign between omega t and kx, but here this k term will change. Why? Because it is other medium, the velocity of the wave will be different. That is why the value of k will change, right. You know, the value of k is the wave number. Wave number is defined as omega divided by v, right. Omega is the angular frequency that remain unchanged and v is the wave velocity, and wave velocity is the solely factor of the medium property. So, here we can write the equation for the transmission wave or transmitted wave, or you can say refracted wave, that is y3 equal to a t sin omega t minus k2x, right. Here a t is the amplitude of the transmitted wave. Okay. Now, let us consider this wave, the incident wave is reflected at x equal to 0. That means, the x coordinate of this boundary is x equal to 0. X equal to 0 is taken only for simplification of the calculation. Okay. And you know, in medium 1, we have the two waves. One wave is the incident wave, which is continuously moving toward positive x direction, and reflected wave is continuously moving toward the negative x direction. That means, in medium 1 we have the superposition of the two waves. One is the incident wave in the positive x direction traveling, and this is the reflected wave which is traveling in the negative x direction. Okay. And but in medium 2 we have only one wave, that is the transmitted wave or refracted wave. That means, if we consider the displacement of any particle situated on the boundary, suppose if we consider point P here, and if we are interested to calculate the displacement of point P, we can calculate the displacement of point P either from the property of medium 1 or property of the medium 2. If we calculate the displacement of point P using the property of the medium 1, the displacement of this is y1 plus y2. Why I have written y1 plus y2? Because in this medium we have the superposition of these two waves, and y1 and y2 represent a displacement that is perpendicular to the direction of wave traveling. So, this is y1 plus y2 is the displacement of point P at x equal to 0. And if we calculate the displacement of the same point by using the property of the medium 2, and in medium 2 we are having only one wave, so we can write this displacement as y3. Okay. Now, we can say, because of the continuous nature of the wave, the resultant displacement on the two sides of the interface should be equal. That means, we can write y1 plus y2 equal to y3, because one point cannot have the two displacement. So, we can write y1 plus y2 equal to y3, and it is at x equal to 0. Now, we know the value of y1, this is the value of y1, this is the value of y2, and this is the value of y3. Now, we can substitute these values, and here we are interested at x equal to 0, right, because we are interested to calculate the displacement, that is the value of y at x equal to 0. So, if we substitute x equal to 0, this will be 0, and this will also be 0, and this will also be 0. That means, we have the sin omega t, and sin omega t on the both side. These terms will get cancelled. That means, now we have the simple equation, simple linear equation in term of AI, AR and AT. Now, we can write AI plus AR equal to AT. Let this equation as equation number 4, because we have numbered up to equation number 3, right. Now, consider this curve again. We know, because this curve is a continuous curve, if we want to find the slope of tangent at this position, suppose at point P again, we can find the slope again by using the property of the medium 1 and property of the medium 2. If we want to calculate the slope at this point by property of the medium 1, we should consider the superposition of the both wave y1 plus y2. That means, we can write now this slope as dy by dx. That means, dy by dx of y1 plus y2, because here we have y1 plus y2, right, and we are calculating the slope, and here we have y3. That means, the slope of this line calculated from this property should be equal to d by dx. This is y1 plus y2, and slope calculated from property of this medium, this slope should be equal to d y3 by dx, right. Now, we can write at x equal to 0, the slope calculated from first part, that is the medium 1, should be equal to slope calculated from the second medium, right. Now, we have y1, y2 and y3, these values we need to differentiate with respect to x. Remember, here there are two variables, that is t and x, right, but we are considering certain instant of the time, that means t is constant. If t is constant, we can differentiate this equation partially. That is, if we differentiate this equation partially with respect to x, the differentiation will be equal to, that is ai cos omega t minus k1x multiplication differentiation of this with respect to x, that is equal to minus k1x. So, differentiation of this y1 equal to this much. Similarly, let us differentiate this term with respect to x again. So, this will be equal to AR cos omega t plus k1x, and differentiation of this with respect to x give the value of k2. So, this is this one, right. Now, final term is y3. The differentiation of this with respect to x will be equal to at cos omega t minus k2x, and differentiation of this equal to minus k2. So, finally, we can write this one, right. Now, where we are considering at x equal to 0. That means, if we substitute x equal to 0, this will be 0, this will be 0, and this will also be 0. That final equation we will have this much. And here we can observe this term and this term will get cancelled, right. We have the simple linear equation in term of AI, AR and AT again. Let this equation number 5. Now, let us do one thing. Let us write equation number 4 and equation number 5 to the next page. Now, we will solve these two equations to get the value of AT and AR. Let us do one more thing. Let us calculate the amplitude of the reflected wave and refracted wave in term of the wave velocity, because generally we are given the wave velocity of the medium. So, we are interested to calculate the amplitude term in term of wave velocity. So, let us write this term in term of the wave velocity. You know, this is the wave number. Okay. Wave number, and this wave number k can be written as omega divided by v. Omega is the angular frequency and v is the wave velocity. And we know this property, that is the omega remains same in all medium when wave is traveling. That means this value is same, and here for the medium 1 this value will be v1, and for medium 2 this value will be v2. So, let us write the value of k1 k2 in term of v1 and v2, this much, right. Now, this omega will get cancelled, and final we have ai divided by v1 minus ar divided by v1 equal to at divided by v2, right. And if we multiply by v1, this equation will finally can be written as ai minus ar equal to v1 by v2 multiplication at. Let this equation number 7. Now, we can solve equation number 4 and equation number 7, right. And now, after solving, we will get the value of first reflected wave, the amplitude of the reflected wave as v2 minus v1 divided by v2 plus v1 multiplication ai, and value of at equal to 2 v2 divided by v2 plus v1 multiplication ai. This is the amplitude of the reflected wave, and this is the amplitude of the transmitted wave. Now, let us discuss few important points. Let us write the amplitude of the reflected wave and transmitted wave again. This is the amplitude of the reflected wave, and this is the amplitude of the transmitted wave. Okay. You can observe here the amplitude of the reflected wave or transmitted wave is always less than the amplitude of the incident wave. Why? Because intensity is proportional to the amplitude square. That means energy associated with the wave is directly proportional to the intensity, and finally intensity proportional to the amplitude square. That means the energy of the wave is related with the amplitude. When a wave reflect at a boundary, that means certain part of the energy reflect back to the medium, same medium again, and certain energy part will move to the medium 2. That means energy will divide into two parts. That's why the amplitude of the reflected wave and transmitted wave will be always less than the amplitude of the incident wave, right. Now, let us analyze one more thing. Suppose a wave is traveling from one medium to other medium, right, and suppose take one special case, medium 1 is rarer and medium 2 is denser. You know, in the rarer medium velocity of the wave is greater, and in the denser medium velocity of the wave is slower or lesser. That means if v1 is greater than v2 and wave is reflected at the boundary, and what will happen to the amplitude of the reflected wave and transmitted wave, right. If you observe these two equations, here v2 minus v1, if v2 is less than v1, that means this value will be negative. Reflected wave means wave is traveling back to the same medium. Transmitted wave means there is no change in the direction of the wave. And here you can observe there will be no change in the sign, because V2 is having the positive value, V1 is also having the positive value. That means the amplitude of the transmitted wave is less than the amplitude of the incident wave, but direction will remain unchanged. And here the direction will change, and also the sign of the reflected wave amplitude will differ. That means it will become from positive to negative. Okay. And this type of the situation occur when two strings tied side by side like this. You can observe here, this is a thin string and this is a thick string, right? And in thin string the linear mass density is less, and you know the wave velocity in the string is v equal to under root t divided by mu, right? If two strings are connected side by side, value of t will be the same. That means here you can write v is inversely proportional to root of mu, right? That means if mu is greater, wave velocity will be less, and here wave velocity will be lesser than wave velocity of this. That means in the thinner string wave velocity will be greater and thicker string wave velocity will be less. And now if we substitute the value of V1 and V2, you know V2 is less than V1, that means the amplitude of the reflected wave will be negative. Magnitude wise it will be less than the incident wave amplitude. So now we can say this wave, that the reflected wave will have the negative sign. Negative sign means, suppose we have the wave equation like this, y equal to a sine omega t minus kx. Suppose we have this equation of the incident wave, and now the displacement, or you can say this value became negative. If suppose we write minus ar sine omega t minus kx, you know from mathematics we can write ar sine omega t minus kx plus pi. That means we can say the reflected wave will have the negative value and it will suffer the phase change equal to pi, because you can observe here the phase is omega t minus kx and here is the phase omega t minus kx plus pi. That means you can say the reflected wave will change its pattern from positive to negative and it will change the phase by pi. It will be like this. Okay, it will start moving in the backward direction and revert, that is phase change of pi. If we consider the opposite case, that means wave is traveling from thick string to thin string. That means V1 is less than V2. That means medium 2 is rarer and medium 1 is denser, like this. Okay, if you observe this equation, now V1 is less than V2, that means the reflected wave will have the reflected wave amplitude will have the positive value. That means the pattern of a reflected wave will not be inverted. That means there will not be any phase change of the reflected wave, but amplitude of the reflected wave will always less than the amplitude of the incident wave. And here there will be no change in the sign because all are having the positive value, but the magnitude of this transmitted wave also less than the magnitude of the incident wave, right? So now we can make the pattern of the wave. It will be like this. It will start traveling in the negative x direction, but direction of the oscillation will not change like this. Okay, so this is the pattern of the reflection at the boundary. Okay, now let us consider one very important case, that is the reflection of the wave from fixed end. Suppose we have one string and string final end is tied with a fixed support or rigid support like this. This is the fixed support or rigid support. Okay, we can consider this rigid support as another string having the great density, very large density, that is density tends to infinite, that is mu tends to infinite we can consider. Okay, and we express the wave velocity v equal to under root t divided by mu. So in the second medium you can take this as a first medium and this fixed support as a second medium, same as these two strings, right? So we can write v2 equal to t divided by mu2 and this mu2 tends to infinite, and if this value tends to infinite, that means V2 tends to 0. If you substitute V2 equal to 0 here, you can observe here this value will also be 0, this will be 0, and this reflected amplitude will be equal to minus of the amplitude of the incident wave. That means if there is no loss of energy, the total energy will reflect back to the same medium. That means the total energy will reflect back. That means the wave will start moving in the negative x direction, and you can observe here the sign of AR will be negative. That means here you can say there will be the phase change of pi, right? This AR equal to AI, and this will be the pattern of the reflected wave, and there will be the phase change of pi. Okay. Now consider one more case, that is a reflection of the wave from free end. How to make the free end? We can do one thing, we can tie a ring to the terminal end of the string like this. This is a rod, and what we have done, we have connected a ring, and the ring is connected the terminal end of the string. Suppose this pulse or wave is incident on the ring, then what will happen? The ring will start oscillating, but there is no part of the string on the other side. That means we need not to consider about the transmitted wave. Now we are considering what will happen to the incident wave, right? Now here we can relate this situation as mu2 equal to 0, because there is no string, we can consider the mu2 equal to 0, and if we substitute mu2 equal to 0 here, the V2 tends to infinite, right? And if V2 tends to infinite, now we can say the reflected wave from free end will reflect back, but there will be no change in the amplitude sign, right? Because this, if V2 tends to infinite, we can write like this. Suppose this equation can be written as AR equal to 1 minus V1 by V2, and this is 1 plus V1 by V2 multiplication AI. And if this V2 tends to 0, if we substitute V2 equal to 0, that means AR equal to AI. That means the amplitude of the reflected wave will be the same as the amplitude of the incident wave, and sign of the oscillation of the medium particle will remain same. There will be no change in the phase, right? So we can make the pattern of the wave like this. So this is the situation when wave is reflected at the free end, right? Now consider one very important thing, what fraction of energy is transmitted to the other medium. So these are the amplitude, the reflected and transmitted wave, and now we are calculating the fraction of energy transmitted to other medium. And we know I, that is the intensity of the wave, is directly proportional to the amplitude square, right? Why we are considering this? We are considering here other thing remain constant as the frequency and other factor, density factor. So we can write I is proportional to the amplitude square, and here we can make this proportionality constant as K. Suppose we write here K. So I is equal to K AI square for the incident wave, right? And for the reflected wave, we can write AIR equal to K multiplied by AR square, right? Now wave incident on the boundary, certain part of the energy will reflect back and certain part of the energy will transmit it to the other medium. That means loss of intensity by the way of transmission will be equal to AI minus AR, right? That means this is the part of the energy that is going to the second medium, right? Now we are interested to calculate the fractional loss. That means we can divide II minus IR with the II, that is the initial intensity. This can be written as 1 minus IR divided by II, and this intensity is proportional to the amplitude square. So this can be written as 1 minus AR divided by AI square, right? Now we know these two value, we can substitute. We can write the value of AR from this equation. finally we will get this type of the equation. So, this is the fraction of energy reflected, this is the fraction of energy transmitted to the other medium. Okay.